Okay, good morning. Welcome back. Happy Chilly Friday. Today is our second to last class of the semester. Uh, we, yeah, that's okay. The most important 5 people are right here, and we're moving on. Today's our last day of new material. We're going to cover a few theorems about definite integrals. I don't think today will be anything too challenging. Coming up on Monday is our review day for the final exam, which is scheduled for Tuesday. Again, our exam is on Tuesday, not a Monday, Wednesday, or Friday. 8 o'clock to 10 o'clock right here in this room. Also on Tuesday, the final project of the semester will be due. Any questions on the calendar? I've already gotten a couple of folks that have turned the final project in. So again, if you've got time this weekend to kind of bang it out and get it out of the way so it doesn't interfere with your studying for final exams and doing other things like that. Okay, so let's take a look in the packet. We're going to take a brief look at page 73. Oh, just while the calendar's here, I'm going to hand out the last take-home quiz of the semester. You'll work on it over the weekend and turn it back in first thing Monday. Okay, so I'll do that later today. All right, so before we jump in with the material, I just wanted to jump to page 73. 73 is the study guide for the final. I don't know how much folks have been making use of the study guide where it's got like the list of things that I'd like you to be able to do coming into the exam. But I think it's something that you can get a lot of use out of if you know how to use it. So for example, if I were to take a look at number 13, it says, I want you to be able to use implicit differentiation to find derivatives for an implicitly defined function. So to be prepared for this final, I want you to be able to go through this list and be able to imagine the kinds of problems that I'm going to ask you, and then have a process in your mind that you follow for each of these kinds of problems. And so for number 13, well, there's a lot of vocabulary here. So the first thing is, do you know what it means to have an implicitly defined function? If you have an equation, you know what you're looking for, that would indicate it's this technique. So somebody tell us here, what will the equation look like? It will have a y in it. What else? That's it. So the x's and y's are going to be all mixed up together, potentially y's on both sides of the equation. So now I'm starting to get the flavor. Oh, it's those kinds of things. And the idea with these, and again, I want you to get to a place where you have in your mind, oh, okay, here's the process we're going to follow. And so the process you're going to follow for this is you're going to take a derivative of both sides of the equation. That's going to involve using like normal ordinary rules. If it's like an xy, what rule are we going to use to take a derivative? Is a product rule, right? So these product rules kind of sneak up on you in these implicit problems. And if there's y's on both sides, take a step back. Every time you take a derivative of a term with a y in it, what do we tack on? The dy dx, right? That's the chain rule saying times the derivative of the stuff. And if there's y's in multiple places in this equation, then we're going to have multiple dy dx terms. So now I'm imagining an equation where some of the terms have dy dx and some of them don't. And then we need to know the algebraic piece in order to get dy dx by itself. So does anybody remember in English that process? We're going to factor. We need to get it so that we can factor dy dx out of all the terms on one side of the equation. What that means is move all the dy dx terms to one side by adding or subtracting, and move any term without a dy dx to the other side of the equation. And in doing so, we've got only dy dx terms on one side, and then we can factor all of these dy dx's out to make a single dy dx times some complicated gobbledygook. And then finally, how do we solve for dy dx? Yeah, so we factored out the dy dx times a bunch of stuff. So then we divide by that whole bunch of stuff, right? And that's it. And then the last piece of this one is that it is quite common to have x's and y's in the answer, right? Dy dx equals x's and y's all together, not just x's anymore, but x's and y's. Okay, so that's the kind of thing that I want you to be able to, this is where I want you to get before the final exam, is to be able to look at each of these 22 things, imagine the kinds of problems I'm going to ask, and then know the process. And so we just did describe the entire process. It's a lot of work to get to a place where you can recognize, oh, here's what all the words Ian is talking about means, and here's the kinds of problems you might ask, and here's the process. But I think that's the key to success, is like understanding the fundamental processes given the words. I think it's all well and good to do practice problems, and there's a couple of practice finals in the pages after this one. But the practice problems ultimately, like if you're not making the connections, it's like, oh, this is how we do all of the implicit differentiation functions. Then you might be really good at that particular problem, but might not be able to apply that same skill to a slightly different looking problem that you face on the test. Okay. All right. So let's go back a few pages and tackle the new material for today. It's here, page 69. At the top, in this class, we discover several theorems about definite integrals and investigate the area between two curves. Okay, number one says a take-home quiz is being handed out today. Make sure you get one. I have not handed it out, but I will. And again, that will be due first thing on Monday. Number two, what if the limits of integration, remember the limits are the numbers that are on the integral sign, right, from something to something. What if the limits of integration of a definite integral are both the same number? What if the smaller number is on top? Here's what we do for each case. Okay, the integral from a to a of some generic function f of x, just think about it. That symbol means find the area under f of x and above the x-axis between x equals a, some vertical line, and x equals a. How much area is in that space? 0, right? Doesn't matter what the function is. If the two limits on the integral sign are the same, it's got to be 0. Okay. Oftentimes, we say the integral from a at the bottom to b at the top, but the limits might be reversed. There's nothing special about alphabetical order here, but the limits might be a bigger number on the bottom and smaller number on the top. Let's take a quick look at an example. Suppose that I tell you that I've got somebody here who is traveling at this is the velocity and this is time, traveling at a constant 6 miles per hour. Somebody's out for a run, 6 miles an hour. And I want to know, like out here to 2 hours, something like that. They go for a 2-hour run. So what I'm calculating here is the integral from 0 to 2 of the function plane 6, constant function, dt. What is that equal to in this case? 12, right? It's just 6 times 2. The area of that little rectangle there is 12 miles. Fair? Okay, but what if instead of asking you for that integral, which is easy, I gave you the integral from 2 to 0 of the same constant 6 function dt. What's the area? It's still 12, but the answer to this one is not 12. The answer to this one is negative 12. And this is just the definition. Definition just says, hey, if you want to swap the numbers on the integral sign, you just take the opposite of the answer. But I want it to make sense. If you imagine like you have a videotape of this runner and you are watching this runner from the start of the videotape at the 0-hour mark until the end of the videotape at 2 hours, or maybe you don't have like a videotape, maybe it's like an overhead of the map and you just like sort of see their route as time passes, you will see that they have covered 12 miles, starting, ending, 12 miles. But if you watch the videotape in reverse, starting at 2 hours in and then watching the videotape backwards, it will appear that they have gone backwards 12 miles. And so negative 12 hopefully is a reasonable definition for that. Okay, so then if I want to make this general, this thing here compared to this thing, which is the same but the limits are reversed, how do I make it so that they are equal? Put a negative sign. So that's it. So anytime you want to change the order of the limits of integration, just make it negative. Okay, so let's try 2 examples where we apply those definitions. Integral from 3 to 3 of x plus 2 dx, 0. Easy, easy. Okay, the next one, integral from 1 to 0 of the square root of 1 minus x squared dx. Okay, so that square root of 1 minus x squared, I have very nicely given you a partial graph of that function. And we're looking between 1 and 0. So what we're really interested in is the area of that quarter circle. Okay, so let's write down the area here. 1/4 pi is good. Number pi r squared and the radius is 1. The whole circle has a pi area. So pi over 4. Okay, so pi over 4 would be the answer. However, it's negative because this is going from 1 to 0. Big number to small number. We really want to think of this as being the other direction. I'm going to write a step that I'll never need you to write. Really, the thing in blue is 1/4 pi. That's what's equal to 1/4 pi. How do I make them equal? Let's put a negative in front. So it's not 1/4 pi, but rather it's negative, okay?
Still with the negative sign if you would add 1, 0.
Yes.
So
Yeah, because the smaller number is on the top, which is not how we define things. So I don't need you to write this, but I do need you to put a negative sign in there. Okay, number 4 has a few properties for us to fill in. Let's actually start with part C. It says the integral from a to b of a constant times f of x dx. Constant times f of x dx. What we want to do is compare this to the integral of just f of x dx. Now, they aren't equal, but I want to know how they relate to each other. So imagine you got this constant times your function. So like you've got little rectangles, right? We're imagining rectangles to approximate the area under the original function. What happens to the height of the rectangles when I do this c times f of x? They just multiply by c, right? So all of these rectangles become c times as tall as they were, which means the area is just c times what it used to be. So in the same way that when we did derivatives, constant multiples can just come out in the front and hang out, it's also true for integrals here. Constant multiples can just come out to the front. Okay, part A talks about the integral of f of x plus g of x. And so what I'd like to do is compare this to the integral of f of x and the integral of g of x. I want to really be able to separate them if possible. So if you think about the area under f, it's got its own little rectangles. The area under g has its own rectangles. The function f plus g is going to have maybe taller rectangles, but it's just going to be like the f rectangle stacked on top of the g rectangle. Is that fair? So what symbol can I put in between to make it equal? It's just a plus. I can completely separate these two functions because they're added together. Just like with derivatives, how do you find the derivative of x to the 5th plus x to the 4th? You do them completely separate. We don't even think about it, but that plus sign makes it very easy. But if it was x to the 5th times x to the 4th, you can't just separate them, right? You need to do a product rule or some algebra or something. Okay, I'm going to get a little bit lazy here and say that addition and subtraction work exactly the same way. Okay, part D has the same function f of x inside of both integrals. The first limits go from a to c. I don't know what c is, a to c. And then the second one is from c to b. And these two integrals are added together. So this picture down here at the bottom left is supposed to help us figure out what's going on here. So this thing represents the area from a to c. I'm going to shade that in orange. Fair? And then the other guy represents the area from C to B. We're going to shade that in green. So can you tell me what this is equal to as a single integral from A to B? Fair?
if the graph wasn't continuous, break it.
The functions that we're talking about, we're assuming are continuous for us to be playing with these areas. Yeah. See? So it actually turns out that we could have had C outside of the whole picture. I'll draw kind of the same shape that we had here. So we've still got A at the bottom here, B at the bottom here. I'm going to extend this graph a tiny bit and suppose that we put C way out here. Turns out the theorem is actually still true even if C is outside of the region. Is this what you were asking about, Levi? What do you mean share a point? The same function. Yeah. Yeah, it has to be the same function that we're talking about, f of x. Yes. The C is the common point for both. Yes. Yeah, so in this case, the first integral, I'll shade it in orange. It's from A to C. So that means it's the entire thing. Yes, that's A to C. And then green is C to B, which I will do this. Does it work? Is it really just the integral from A to B? Can we like double shade part of it? A to C would count the orange, but then C to B would count the green, which is right on top of the orange. But it's negative because if C is way out here, then C to B is the quote wrong order, right? It's a big number to a small number. And so going C to B is backwards, which subtracts all of that green area. And you are left with exactly the stuff between A and B, which is what we wanted. Okay, so we can apply that theorem here in or some of these theorems here in number 6. It says evaluate this integral from 0 to 1 of 5 minus 3 times the square root of 1 minus x squared dx. Okay. First and foremost, this problem right here is a subtraction problem, yeah? And subtraction for integrals is really nice. We can just separate into two integrals. So let's begin there. 0 to 1 of 5 dx minus integral 0 to 1 of 3 root 1 minus x squared dx. Don't forget, every integral has to have a dx usually, could be a dt. But every one of those has a d something at the end. Okay, this first integral is actually pretty easy. 5 is a constant function, right? And we're just going from 0 to 1. So what's the area there? It's 5, right? 5 times the 1. Okay, so this one, I'm just going to put 5 times 1 minus 0. It's just 5. Okay, minus. All right, how can we clean this up? Josh? Yeah, we've done the square root of 1 minus x squared, but the 3 is in our way. That's the idea. So I'm going to write out this step here. And that's our fun little rule, right? Is that the constant multiple can come outside. And as Josh points out, we've already calculated that particular integral. What was that integral equal to from our quarter circle thing? Was pi over 4? Was it positive or negative? Is this one positive or negative? This is going from 0 to 1. That's the, quote, right order, right? Because it's from a small number to a bigger number. Okay, so we're good here. So 5 minus 3/4 pi is our answer. Okay, so real quick, we'll see if the calculator agrees with us. I'm just going to type in 5 minus 3 square root 1 minus x squared, comma, x, comma, 0, comma, 1. What's the calculator going to tell us? Yeah, calculator has no chance of doing this, right? In fact, the calculator is not doing any of the stuff that we did. The calculator is using like 1,000 rectangles and approximating the area under this particular function right here. Okay, how will I see if our answer agrees with that answer? Yeah, I'll type in our answer, right? 5 minus 3/4 pi. Doesn't quite agree. I mean, it's close. Which answer is more accurate? Yeah, I mean, this is the exact answer. So our decimal is more accurate than that one. And it's not perfect. They're not doing any calculus. They're doing 1,000 rectangles. And there's going to be some error involved usually. Okay, I think that is good. Let's move on to the activities, which are right there on the next page. I will walk around.